Section 2.7 is going to have a handout for you to take notes on, so make sure you have that handy. And we're going to talk about absolute value functions and what their graphs look like. So we're going to talk about the parent function for the absolute value family, and that's this little guy. It looks like f of x equals the absolute value of x, or it could say y equals the absolute value of x. So what we're looking for to know that a function belongs to this family of graphs and has a distinct shape that is given by this equation is the bars with the variable x in it. And so what we're going to do to think about the shape of it is think about absolute value. Absolute value means the distance from 0 on a number line. So if I put 0 in for x, how far is 0 from 0 on the number line? It's 0 units, so y would be 0. If I put 1 in for my x, 1 would be 1 unit away from 1, so y would equal 1. If I put 2 in, 2 is 2 units away, so I would go up to 2, and 3 would be 3, and so on and so on. Then if I put in -1 would also be 1 unit away from 0, so -1 would go to 1. -2 is 2 units away, so -2, 2. And -3 is 3 units away, so -3, 3. When we're graphing these absolute value functions, we don't want to have to think about how to figure out the ordered pairs each time. So we're going to memorize a pattern. The pattern is going to be that we have a vertex at 0, 0, and then the way that we graph from there is we are going to go right 1, up 1, and then we go back to the vertex, and we go right 2, up 2, and then we go back to the vertex, and we go right 3, up 3. The graph has symmetry across a vertical line through its vertex. So you also need to graph the corresponding points. So that would be the ones left and up on that side. Then we're going to connect our dots using a straight edge. And what we want to do is go all the way to the edge of whatever graph paper we're given and make those nice and neat and also accurate. So that is what the absolute value function looks like. So any equation that would have those bars in it is going to have this classic kind of V-shaped graph with a vertex. Now it might be skinnier, it might be wider, it might be upside down, it might be shifted up, down, left, or right, which is what we're going to learn about today. So let's talk about these transformations. Transformations could include shifts up, shifts down, shifts left, shifts right, reflecting in the x-axis or the y-axis, or a vertical stretch or compression. So these transformations, if you have all of them in here, then this is where they would be located in your equation. So we'll talk first about the shifts. What happens with a shift is it's going to change the location of the vertex, which is where we start our graph. So if I shift my graph to the left and down, then that's where I will start from, and then all other points will also end up being shifted left and down. So to figure out which direction to go, we would look at the equation, and what you'll see is that we would have, to shift up and down, we would have a number either added or subtracted after the absolute value. So if I have a number added after the absolute value, it's going to shift the graph up by that many units. If I have a number subtracted after the absolute value, it's going to shift the function down that many units. But if I have a number added inside the absolute value, it's going to shift the graph left. So one way to think about that is to take your stuff that's inside this absolute value and set it equal to 0. So x plus h equals 0, and then we get x equals negative h. That will give you the x-coordinate of your vertex. Similarly, if I have subtraction inside with the x, it's going to shift my graph right h units, which again, if I set x minus h equal to 0, I would add h to both sides, and that would give me positive h. Another way to think about it would be that if the number is stuck inside with the variable, it's kind of like being grounded. And so, like, if your parent function, absolute value of x, tells you plus h, which is like adding, then you're going to do the opposite, which is to go to the left, kind of like subtracting. So if it's inside with the x, you're going the opposite direction it says. If it's outside of the bars, you're going to go the direction you would naturally think, so plus would be up. But if it's stuck inside, plus would be left. And if it's stuck inside, minus would be right. So all 4 of these are going to change the location of the vertex, which will also in turn change the location of the entire V shape. If you have a negative sign out in front of the absolute value symbol, that is going to reflect the graph in the x-axis or across the x-axis. So what we would do is, you can think of it as multiplying the ups by 1 or turn the ups into downs, whichever way makes sense to you. But it's going to effectively make your graph reflect in the x-axis, which will make it open down instead of opening up. If you have a negative sign inside your absolute value, that is going to reflect the parent function in the y-axis. Well, if you take this V shape and flip it over the y-axis, it's not going to change how it looks. What that effectively does is you multiply your overs by negative 1. So instead of going right 1 up 1, I go left 1 up 1. But then remember, because of the symmetry, I'm going to also do the other points. So reflecting over the y-axis does not change the absolute value shape. That one will look the same. We still need to say, oh hey, we're reflecting across the y-axis, but it won't change the way the graph looks. And then we have vertical stretches and compressions. These are the ones that make the 2 parts of it either be steeper or less steep. So if you have a number multiplied out in the front, when that number is bigger than 1, like 3, or it could also be negative 3, because remember the negative is doing a reflection, so a negative 3 would be 2 different things. It would be reflecting, but then also this stretch. So when a is greater than 1, you have a vertical stretch of the parent function, and so we're going to multiply all of our ups by that number a. So when we have a vertical stretch, it makes it taller and skinnier. But when a is between 0 and 1, because we're ignoring the sign, then you get a vertical compression of the parent function. And what that does is it makes the graph kind of less steep. So it's like shorter and wider than it normally would be. So what we'll do here is we will practice looking at some equations and tell what the transformations are, and then we're going to graph them. So let's look at, oh, I did not label these overs and ups. These guys here are the overs, and these guys here are the ups, because we're going over 1, over 2, over 3, up 1, up 2, up 3. Okay, so let's look at our examples. We're supposed to say the transformations, list the vertex and describe how to graph the function, then graph it. So in our parent function of f of x equals absolute value of x, anything that is not an f or the parentheses x or the equal sign or the two bars or the x, everything else you see in here has to be accounted for by a transformation. So I can ignore the f of x and the equals, I can ignore the bars and the letter x, so I have to pay attention to this plus 3 that's inside and this minus 5 that's outside. If I'm adding 3 on the inside, I'm going to look at my possibilities. These guys are multiplies, these guys are negative multiplies, and these ones up here are the adding and subtracting. So this is add 3 on the inside, which looks like this one right here, and this is telling me that it shifts my parent function left h units. So here I have plus 3 inside, so this is going to shift my graph left 3 units. And then the next thing I need to account for is this subtracting 5 at the end. So subtracting 5 after the absolute value bars is this one right here, which says it will shift my parent function down k units. So since I did minus 5, it's going to shift down 5 units. So my transformations are that it's going to shift left 3 units and shift down 5 units. So that's the first part. The second part is I'm supposed to say where the vertex is. Well, the vertex normally starts from where? Normally the vertex starts at 0, 0. So my vertex starts at 0, 0, but then it's going to do this shifting. So instead of starting at 0, 0, it's going to shift left 5 and then down 3. So it's actually going to go to the ordered pair, left 3 and down 5. My mistake. Left 3 and down 5. So instead of starting at 0, 0, it's going to start right here at negative 3, negative 5. Then how do I graph it? Normally I graph it by going over 1, up 1, over 2, up 2, over 3, up 3. And then what's going to change possibly my pattern would be the reflections and the stretch and compression. So the shifts up, down, left, and right change the vertex. The reflections, stretches, and compressions change the pattern. So I have to say, are there any stretches, compressions, or reflections? If I look out to the front, there's no number out in front, so I don't have any stretches or compressions. I don't have any negatives out in front, or a negative in front of my x. So since I have no stretches or compressions, my pattern is going to be normal. So from my new vertex, I will go over 1, up 1, go back to the vertex, over 2, up 2, back to the vertex, over 3, up 3, and then I need those same points on the other side of the vertex. Then I will connect my dots all the way to the edge of my graph paper using a straight edge, and that will be my graph. The next one over here, part 1, identify the transformations. So I'm going to remember that anything that's not the f of x equals bar x bar, everything else is a transformation. So I can ignore f of x equals and this bar x inside. I have to pay attention to the 2 times out front and the plus 1 at the end. The 2 times out front is going to be this one right here, or this one right here. If a is bigger than 1, it's a stretch. If a is between 0 and 1, it's a compression. So just think of it like it's multiplying your height by that number. If I multiplied my height by a number bigger than 1, I'd get taller. If I multiplied my height by a number between 0 and 1, I'd get shorter. So getting taller is a stretch, getting shorter is a compression. So this 2 times out front is going to be what we call a vertical stretch of 2. And then I can ignore the bar x bar because that's just telling me what shape I'm going to have. And then I have a plus 1 at the end, which we've already seen one like that. That's this guy here, which shifts up 2 units. So my other transformation is to shift up 1 unit. How do I graph this guy? Well, first I want to know where the vertex is. It's normally at 0, 0, but I'm going to shift up 1 unit. So instead of being at 0, 0, it is going to be at 0, 1. And then from there, normally I would go over 1, up 1, back to the vertex, over 2, up 2, back to the vertex, over 3, up 3. But since I have a stretch, what I need to do there is multiply all my ups by that number. So I'm going to multiply my ups by 2. So times 2, times 2, times 2. So I'm going to go over 1, but then I'm going to go up 2. So to the vertex, over 1, up 2. Then I go back to the vertex, and I'm going to go over 2, but now I'm going to go up 4. Back to the vertex, over 2, up 1, 2, 3, 4. And then instead of going over 3, up 3, I'm going to go over 3, up 6. So back to the vertex, over 3, up 6. And then I have those same points on the other side of the vertex. And then grab your straight edge and draw your graph. Something else we need to figure out how to do is to write the function that represents given transformations of our parent functions. So what we will do is we'll go backwards. We're going to get a list of transformations, and we have to write the equation and then also identify the vertex and describe how to graph it. So our transformations are to stretch by a factor of 3, shift left 4, and up 5. So if I'm going to stretch by a factor of 3, stretching means that I have a number times out front. So I need a 3 times out front. Then I need to shift left 4, shifting left means that I need to add that number inside the bars. So I need to do plus 4 inside, and then up 5, up means that I need to add that number after the bars. So I need to do plus 5 after the bars. So my basic function was f of x equals the absolute value of x. So I start with f of x equals, and then I know I'm going to have absolute value of x, but then I need to do 3 times out front, so I'll have 3 times. I need to do plus 4 inside, so x plus 4 inside the bars, and then I need to have plus 5 after. So at the end, I will add 5. Now as far as graphing this goes, the vertex is normally at 0, 0. But since I have a shift left 4 and up 5, it's not going to be at 0, 0. I need to go left 4 units, which takes my x value to -4. And I need to go up 5 units, which takes my y value up to 5. So my vertex is going to be at negative 4, 5. Then normally to graph, I would go over 1, up 1, over 2, up 2, over 3, up 3. But I have a stretch of 3, so I need to multiply all my ups by 3. So then I'll go over 1, up 3, over 2, up 6, over 3, up 9. That may not all fit on my graph, but that's okay. So on my graph, I will start at negative 4, 5. From that vertex, go over 1, up 3, go back to the vertex, over 2, up 6, and then those mirrored points on the other side. That's all that's going to fit on there. So I'll just graph that V shape that makes the absolute value family and call it good. Let's try another one. This time we're going to compress vertically by a factor of 2/3, reflect in the x-axis, so that's the first one we've seen of that, shift right 1 and up 8. So we just saw a stretch up here of 3. Compressions are going to be in the same location. So I'm going to have a 2/3 out front. So let me get my basic function here. Remember, the parent function is f of x equals bar x bar, and then everything else is going to be transformations and needs to be accounted for in there. So compress by a factor of 2/3, that's going to be 2/3 multiplied out front of the absolute value bar. Then reflect in the x-axis. Since we haven't seen that one before, let's look back at our other side. So we have two kinds of reflections: reflect in the x-axis, reflect in the y-axis. When we reflect in the x-axis, that negative sign goes out in the front. Now I already have a number out front there. So since there's already a 2/3 there, and I need to multiply by a negative when I reflect in the x-axis, I will just make that 2/3 a negative 2/3. Then we are going to shift the graph right 1 unit. Now when we shifted left, we had to add inside. When we shift right, we have to subtract inside. So it's going to be x minus 1. And then up 8 units, we'll just add the 8 at the end like we did with the 5 up there. So how do we graph this? Well, normally we start with a vertex at 0, 0, and then our pattern is over 1, up 1, over 2, up 2, over 3, up 3. But what we're going to do this time is we need to shift right 1 and up 8. So our new vertex to shift right 1, instead of starting at 0, is going to start at 1 for the x-coordinate. And then to shift up 8, instead of starting at 1, 0 or 0, 0, it will be at 1, 8. And then the reflection is going to change all of the ups to downs. So now we're going to be going, instead of up each time, we're going to be going down, down, down. But we also have to deal with that compression. So we need to multiply all of those by 2/3. So 1 times 2/3 is 2/3. 2 times 2/3 is 4/3. 3 times 2/3 is 2. So we'll start with our vertex at 1, 8. And then we are going to go from the vertex, we're going to go right 1, down 2/3. So right 1, down 2/3. Now you'll just have to estimate on your graph. Right 1, down 2/3. And then we're going to go back to the vertex and go right 1, down 4/3. 4/3 is 1 1/3, so we'll go right 2, down 1 1/3. And then go back to the vertex and go right 3, down 2. Back to the vertex, right 3, down 2. And then remember that you have those mirrored points on the other side. And connect your dots using a straight edge. Remember to take your graph all the way to the edge of the grid that you're given. And we have a compressed and reflected graph that has been shifted right and up. Okay, now we're going to start from the graph and write the function that represents the transformations. So let's look at what transformations we have in this graph. Well, remember normally our graph starts with a vertex at 0, 0. But that's not where this vertex is. This vertex is at 4, -8. So my vertex is at 4, -8. Now moving from 0, 0 to 4, -8 represents a shift right of 4 and a shift down of 8. Now let's look at if there are any reflections, stretches, or compressions. Since my absolute value function is in that up-facing V shape, there is no reflection, so I won't have a negative sign out front. But let's check out kind of the pattern here. When I move on a normal vertex, or a normal absolute value, I'll go over 1, up 1. But if you can tell on here, when I move over 1, I'm going to move up 1, 2, 3. So my pattern is over 1, up. Instead of 1, it's up 3. And then if I move over 2 from my vertex, I'm going up 1, 2, 3, 4, 5, 6. So over 2, up 6. And if I follow that same pattern, I would go over 3, up 9. So can you tell what we're doing as far as our stretch? Instead of going by 1, 2, and 3, I'm going by 3, 6, and 9. So that is going to give me a vertical stretch of 3. So if I start with my original absolute value function, f of x equals bar x bar, and then I put all those transformations in there, shifting right, remember, goes inside that absolute value, but I have to do the opposite sign. So to shift right by 4, I have to say x minus 4 inside the bars. Shifting down 8 is going to be after the bars, and it's going to be the normal sign you'd think it was, so it's subtract 8 after the bars. And then vertical stretches are multiplied out in front of the bar, so it's going to be 3 times out in front. And this would represent that function. Let's look at another example. Let's locate the vertex and see if there is a reflection and is there a stretch or compression by the pattern. So the vertex is located, not at 0, 0. The vertex is located at 0, 4. Well, the x-coordinate is the same. It's the y-coordinate is the only difference. So that is a shift up of 4 units, but no shifts left or right. Is my function reflected? Yes, it is upside down. So that is over the x-axis. if you look back at that side over there, these reflections in the x-axis make our graph be upside down. And that's going to mean we have a negative out front of our function, of our absolute value bars. And then let's look at the pattern. So we would normally go over 1, and since it's reflected, we would go down 1. So over 1, down 1. Go back to the vertex, over 2, down 2. Back to the vertex, over 3, down 3. So it does not look like we have any stretches or compressions, but we do have that reflection. So our function would be the regular f of x equals bar x bar, and then put all our transformations in there. Up 4 means we're going to add 4 after the absolute value bar. Reflect over the x-axis means I need a negative times out front. And it looks like those are my only transformations, so it would be f of x equals the opposite of absolute value of x plus 4.